Hello everyone, my name is Hao-Kun Li. It is my great pleasure to be here and share with you our recent research regarding phonon transfer across the quantum vacuum. This research was performed during my PhD study in Professor Xiang Zhang's group at University of California, Berkeley. Now I have moved to Stanford University as a postdoc researcher working with Professor Arun Majumdar in the Department of Mechanical Engineering. First of all, I would like to thank the organizers for hosting such a great conference and providing me the opportunity to present in this session. I would also like to thank all the audience for your interest and attendance to my talk. Let me begin by briefly reviewing the concepts of heat transfer. When two objects are brought to contact, we know that heat is conducted by either electrons or atomic vibrations, so-called phonons. As the two objects are separated by a vacuum gap, in conventional concept, energy is transferred by radiated photons, but not by phonons, because there is no medium in between to assist the phonon transfer. In this talk, I would like to introduce you a mechanism that we recently demonstrated, which allows phonons to transfer across a vacuum gap. This mechanism gives rise a new channel that transfers heat across the vacuum and allow us to better manage heat at the nanoscale. In view of quantum mechanics, vacuum is not empty, but filled with tiny fluctuations of all kinds of fields. Take electromagnetic fields as an example. Although the averaged field is zero, there are always tiny little fluctuations of the fields that exist everywhere in space. These fluctuations can be explained by the Heisenberg uncertainty principle. Given a certain time period, there is always a finite amount of energy that pops out in space, even at absolute zero temperature. Such quantum fluctuations can cause bizarre physical consequences. One important example is that when we put two neutral objects close to each other in vacuum, there is an attractive force between them, which we call van der Waals-Casimir force. So how do two neutral objects become attractive to each other when they are being close? We know that all objects are made of atoms, which are neutral particles consisting of electrons and nucleus. When there are quantum fluctuations of electric field in space, one atom may become polarized at an instant. If there's a second atom nearby, the second atom will be polarized by the first atom because the electron cloud nearby would pull the nucleus closer due to the Coulombic attraction. So we end up with this configuration where the electrons and nucleus are very close to each other, giving rise to attraction between the atoms. By summing all the attractive interactions between all the atoms in the two objects, we can obtain the van der Waals-Casimir force between the two objects. In the short range, which we call the van der Waals regime, the force is inversely proportional to the third power of the distance. While in the long range, which we call the Casimir regime, the force is inversely proportional to the fourth power of the distance. Now we come back to look at our heat transfer problem. Because the objects have finite temperatures, if we zoom in to the surfaces, there is phonon thermal oscillations, which causes the boundary to move. And we know that there is van der Waals-Casimir force, which depends on the distance between the boundaries. The phonon oscillation on the right side can generate a time-varying force that agitates the oscillation on the left side. And therefore, a channel of heat transfer is generated. Effectively, each pair of phonon modes are connected by a spring, and the spring constant is proportional to the force gradient. Over the years, people have been discussing this effect in theory, but it has not been experimentally proved. We decide to experimentally probe this interesting quantum effect by looking at the dynamics of individual phonon modes in nanomechanical devices. Let's consider a clamped mechanical membrane as shown here, and we just look at the motion of the fundamental phonon mode. At finite temperature, this mode is oscillating near a characteristic frequency, with amplitude fluctuating up and down versus time as shown here. The average kinetic energy of this phonon mode is proportional to the mean square of the amplitude. So with this equation, we can define this mode temperature to describe the thermal energy of this particular phonon mode. Now, there is another temperature here, which we call the bath temperature, which is our conventional concept of heat temperature describing the whole body of the mechanical membrane, which include the rest of the phonon mode. And we can measure it by attaching a temperature sensor, like a thermal resistor. If the whole mechanical membrane is placed in vacuum and there is nothing around, this mode temperature is equal to the bath temperature, meaning that the phonon mode is in equilibrium with the thermal bath. There are circumstances where the phonon mode temperature could be higher or lower than the bath temperature. For example, when there is a random force that drives this phonon mode, the phonon mode could have higher kinetic energy than the equilibrium case, meaning effectively that this phonon mode is hotter than its thermal bath. In those circumstances, the phonon mode and the thermal bath would exchange energy through the mechanical damping. The energy exchange rate between this phonon mode and the thermal bath can be estimated by multiplying the mode-bath temperature difference and the mechanical damping rate. Now suppose we place another mechanical membrane with a different bath temperature nearby. The two fundamental phonon modes would couple to each other by van der Waals-Casimir force, and we can control their coupling by adjusting their distance. When we fix the two bath temperatures and try to bring the membranes closer and closer, the mode temperatures would start to deviate from their bath temperatures, as shown by this theoretical prediction. The phonon mode on the cold side would heat up, while the phonon mode on the hot side will cool down. This phenomenon would become prominent when the coupling rate is comparable to the damping rate. A large coupling rate can be obtained by increasing the interaction area between the membranes. In our experimental design, with a lateral membrane size of about 300 microns, the phonon transfer effect becomes prominent with 400 nanometer separation between the two mechanical membranes. The thermal vibration of the fundamental phonon mode of the membrane is on the order of a picometer, which is 100 times smaller than the size of an atom. To precisely measure such a small displacement, we use optical interferometry. Basically, we put a mirror close to the membrane, which forms an optical cavity with the membrane. When the membrane moves, the optical reflectivity will change. With this method, we can resolve the vibration amplitudes and determine their kinetic energies, namely the mode temperatures. In our experiment, the nanomembranes are made of silicon nitride with both sides coated with gold. The samples are placed on a cooler and a heater with temperature sensors so that we can control and measure their bath temperatures. To observe the phonon transfer effect, an important requirement is to match their resonant frequency of the two phonon modes. This is like when you try to listen to radio, you always want to tune your receiver resonant to the station, such that the energy can be transferred effectively. Here, the resonant matching is achieved by adjusting the stress of the membrane with their bath temperatures. In our design, the two membranes have slightly different sizes, so their resonant frequency are different if they are at the same temperature. While cooling one membrane down and heating the other membrane up, we can match their resonant frequencies, and at the same time, we can establish a temperature difference that drives the phonons to transfer. Another important experimental requirement here is to align the two planar membranes with a high degree of parallelism. Because the two membranes with lateral size about 300 microns need to be brought together with a separation as small as 300 nanometers. To achieve this goal, we fabricated the mesa structure on the left chip and 4 electrical pads on the right chip. The red and blue squares at the centers are showing the locations of the mechanical membranes. By adjusting the relative angles between the membranes and making the 4 electrical pads simultaneously touch the mesa structure, we are able to make the two membranes parallel to each other. The parallelism can be further examined by using optical interference effect, with a blue LED penetrating both the membranes. With good alignment, the interference pattern on the membranes would always look very uniform as we change their distance. As we bring the two membranes close, the two phonon modes would start to couple to each other, resulting in two eigenmodes, namely the symmetric mode and the anti-symmetric mode, as shown here. So in the thermal vibration spectrum of each membrane, we observe two peaks. The splitting of the peaks is proportional to the force gradient. By changing the distance between the membranes, the frequency splitting shows a power law that is roughly inversely proportional to the fifth order of the distance. Such a power law matches the power law of the Casimir force gradient. This observation demonstrates the Casimir coupling between two phonon modes for the first time. To demonstrate the energy transfer between the phonon modes, we keep the resonance of the two phonon modes by locking their bath temperatures. At the same time, we measure the displacement of the phonon modes to monitor their mode temperatures. At far distance, the mode temperature are equal to their bath temperatures. When the distance gets smaller, the mode temperatures start to deviate from their bath temperatures, meaning effectively, one phonon mode heats up while the other phonon mode cools down. And eventually, with 400 nanometer separation, the two phonon mode temperature become almost identical, meaning that the two phonon modes have the same thermal energy. The solid lines are our calculation result, which well describe the experimental data. To further verify that the observed change of mode temperature is due to the coupling between these two fundamental phonon modes, instead of coupling between other high-order phonon modes or thermal radiation effect, we offset the resonant frequency of the two phonon modes and monitor their vibration amplitude at short distances. As shown here on the right, without resonant matching, the mode temperatures remain equal to their bath temperatures. This result verified that the observed energy transfer effect on the previous slide is a result of the coupling between the two fundamental phonon modes. It also suggests that the energy transfer can be tuned on and off by controlling the resonant matching. In our experiment, the two fundamental phonon modes are well isolated from their thermal baths, given by their small damping rates, and therefore, we are able to identify their thermal energy exchange by measuring their vibrational energy, namely their mode temperatures, T1' and T2'. The heat flux between these two coupled phonon modes can be estimated with the measured mode bath temperature difference and the mechanical damping rates. To obtain the total heat flux between the two bulk solids resulting from this phonon coupling effect, the contribution of all the phonon modes needs to be considered. Experimentally, such a quantity is remained to be explored. Based on previous theoretical calculations, the total heat flux generated by this phonon coupling effect could be stronger than near-field thermal radiation, with a gap size between 0.5 and 3 nanometers. Such vacuum phonon coupling would provide us a new degree of freedom to control heat transfer across vacuum at the nanoscale, which is very important for many applications, such as non-invasive thermal imaging, thermomagnetic data storage, and nanolithography. In addition, the ability to achieve and control strong Casimir phonon coupling provides a versatile platform for implementing coherent phonon process, such as phonon entanglement and phonon state transfer. To briefly summarize, by looking at the dynamics of individual phonon modes, we have demonstrated phonon coupling across vacuum driven by quantum fluctuations, and observed the thermal energy exchange between individual phonon modes. I would like to thank my PhD advisor, Professor Xiang Zhang, and all my collaborators on this project. This research was supported by U.S. National Science Foundation. Thank you very much for listening. I'm looking forward to all your questions in the Q&A session. If you seek for further discussions, please contact me with this email address. Thank you again for your attendance, and enjoy the rest of the conference.